Welcome to our presentation. I am Abigail Streamo. During our presentation, we delve into the objectives, the methodologies, and insights derived from our analysis focused on predicting early readmission of diabetes patients within 30 days of discharge. Our presentation begins with defining the analysis objectives, understanding the machine learning techniques involved in identifying key features and target variables. We'll explore data preprocessing techniques, feature engineering strategies, model training, evaluation metrics, and model selection methodologies. Our group includes Ryan, Levi, and myself. Our primary objective was clear: to harness the power of machine learning to foresee the likelihood of patients being readmitted within a critical 30-day window. We undertook a supervised learning approach armed with a comprehensive data set that spanned from 1999 to 2008. It involved 46 features ranging from demographic information to medical history. Our initial exploration unveiled a challenge. Missing values and outliers were dotted on our dataset landscape. Notably, features like the race, weight, and medical specialty stood out with significant gaps. To address this, we constructed pipelines equipped with imputers to handle missing data, ensuring robustness in our analysis. In the data preprocessing and exploration, the code first fetches the dataset. It then calculates the total number of rows and identifies the missing values in each feature. The box plots and scatter plots are then plotted for numerical features to identify outliers and understand the distribution of the data. Categorical and numerical columns are separated. The feature engineering steps include age binding and creating new features related to drug interactions, and total medications. Preprocessing pipelines are defined for numerical and categorical features, including imputation and one-hot encoding. The preprocessing pipeline is applied to the data, handling missing values and encoding categorical variables. Dimensionality reduction using truncated SVD is performed. In the model training and evaluation, the data is split into training and testing sets. A randomized search CV is used to tune hyperparameters for a random forest classifier. The best hyperparameters are extracted from the randomized search CV results. A random forest classifier is trained with the best hyperparameters. The trained model is evaluated using classification report to generate a comprehensive report, including precision, recall, F1 score, and support for each class.
Hello, my name is Ryan Strasburg, and I will be going over feature engineering, modeling training, and model evaluation. So to begin with feature engineering, in our project, feature engineering was pivotal for preparing the data for modeling. One significant transformation involved converting age ranges into numeric representations. By averaging the age ranges and categorizing them into groups, young, middle-aged, and elderly, we made it easier for the model to interpret age as a continuous variable rather than discrete categories. Age binning. We applied a transformation to the age feature, converting it from ranges to numeric representations. This involved stripping unnecessary characters, splitting the range, and calculating the average age. By binning the ages into groups, we made the data more manageable and potentially more informative for our model. Drug interaction features. Another crucial aspect was transforming drug features from strings to integers. This allowed for a more nuanced analysis of medication usage. We created binary features indicating whether a patient was prescribed each medication, facilitating a deeper understanding of drug interactions. Additionally, we computed the total medications column by summing up the binary features for each patient, providing an overall measure of medication complexity. So we'll move on to modeling training. So, with our data prepared through feature engineering, we moved on to modeling training. We explored various algorithms to find the most suitable one for our task. Dimensionality reduction: to handle the high dimensionality of our data, we applied truncated SVD for dimensionality reduction. By reducing the number of features while retaining most of the information, we aim to simplify the model and mitigate the risk of overfitting. Model selection and hyperparameter tuning. We initially trained a random forest classifier, a versatile algorithm known for its robust performance. However, to further optimize its performance, we employed randomized search CV. This technique allowed us to search through a range of hyperparameters and find the combination that maximized the model's accuracy. By systematically adjusting these parameters, we fine-tuned the random forest classifier, improving its effectiveness significantly. Okay, we will move on to model evaluation. After training the model, thorough evaluation is essential to gauge its performance and identify any shortcomings. Performance metrics. Our model's performance was assessed using precision, recall, and F1 score, which provided detailed insights into its effectiveness across different classes. Results overview. Despite achieving an overall accuracy of 57%, which might seem acceptable at first glance, a closer examination reveals severe signs of overfitting. This is evident from the significant disparity between the training and testing performance metrics. For instance, while the model achieved relatively high precision, recall, and F1 score for the no class, indicating patients without readmission, it struggled with the less than 30 and greater than 30 classes, showing low recall and F1 score. This discrepancy suggests that the model might be overly complex and has learned to memorize the training data rather than generalize well to unseen instances. And I will pass the baton to Levi.
Okay, I'm Levi Diaz, and some of our reflections and concerns that we have about this is despite our combined efforts and experimentation, such as the deletion of entire columns which had a significant amount of missing values, or using randomized search, and also using model selection through the tweaking of hyperparameters, the model's accuracy plateaued at about a concerning 0.57, hinting that there might be some underlying challenges and problems like overfitting. So the time constraints posed a very formidable barrier for us, and that stopped us from doing as extensive experimentation as we would have liked to have done, and also limited our ability to explore and play around with other models to experiment if we could get better performance out of other models. So if you look here, we do have a concerning score of 0.57, and while some of our other numbers are a bit better, many of them are far from ideal. And so for the future direction of this, if we were given additional time, a roadmap begins to appear in which we could further enhance our performance of our model. The main thing that we'd like to do is experiment with other models and algorithms, which seems as to be the most promising avenue. However, aiming to mitigate and experiment further with our current model, mitigate overfitting by experimenting with our current model also seems to be a promising avenue that we could further explore. That would possibly help with the performance of our model. And then, in conclusion, our journey through this project has been illuminating and very challenging, and while our efforts have yielded valuable insights into the predictive healthcare analytics, the road ahead beckons that with opportunity that we could refine and further improve our model, especially with experimentation of other algorithms. Thank you.